Pluto is a distant and confusing midget planet, once viewed as an individual from our planetary group. However, ongoing provocative remarks from unmistakable astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto into public conversation again with an enlightening disclosure. They recommended that this cold world may set out toward a crash with Neptune. But how could such an event be conceivable, and what might the results be if it were to occur? Might this be an interesting yet misrepresented forecast, or is there a certifiable reason to worry about a horrendous event? Let's dig into the potential outcomes of a Pluto-Neptune crash. Once designated a planet, Pluto was downgraded to a dwarf planet due to its unusual orbit, and it remains a subject of significant interest within the cosmic community. Later observations from top specialists emphasize Pluto's orbit, which is dangerously close to Neptune's. Both Neil deGrasse Tyson and Michio Kaku have raised alarms over the probability of a destructive crash between these two far-off planets, a situation that could pose a serious risk to Earth. But how could such an impact be conceivable? Pluto's journey around the Sun is unlike any other planet in our solar system. It takes an unpredictable 248 years to complete just one orbit, meaning that since its discovery in 1930, Pluto has yet to complete a single full orbit. But that's not all. Pluto's orbit is marked by its irregular, elliptical shape, which significantly deviates from the nearly circular orbits of most other planets. Adding to the curiosity of Pluto's orbit is its 17 degrees tilt to the ecliptic plane, a direction that is much more extreme than the paths followed by other planets. A particularly captivating part of Pluto's orbit is its convergence with Neptune's orbit. For about 20 years during every revolution, Pluto comes closer to the Sun than Neptune, which goes against their expected relative positions in the solar system. This raises the intriguing question: why hasn't Pluto crashed into Neptune? The answer lies in the gravitational influence applied by other planets. Shortly after Pluto's discovery, astronomers began studying its unusual orbit. Unlike the orbits of other planets, which generally lie in the ecliptic plane, Pluto's orbit stood out for its steep angle and elliptical shape. The complexity of Pluto's path became even more apparent as scientists realized it actually crosses Neptune's orbit. Despite these surprising characteristics, Pluto's orbit displays remarkable stability due to the gravitational influences of the solar system's other bodies. The three-body problem in celestial mechanics seeks to explain the gravitational interactions and movements of three celestial bodies, such as Pluto, Neptune, and the Sun. Pluto's path through the solar system is somewhat erratic. Minor changes in initial conditions can lead to major differences in the trajectory over long periods. However, studies have shown that Pluto's orbit has remained stable over extended periods, maintaining control amid the apparent chaos. Simulations have helped us understand how Jupiter's massive gravitational pull, among other factors, ensures Pluto's consistent motion around the Sun for billions of years. These factors are crucial in keeping our solar system somewhat organized and preventing disorder from overtaking it. Pluto's orbit is a striking example of how stability and chaos coexist within the solar system. The forces at play, especially the gravitational impact of neighboring planets like Neptune, highlight the complex and dynamic nature of space. Predicting large-scale events, particularly those involving unstable orbits, such as Pluto's, is incredibly challenging. The inherent eccentricity of these systems makes long-term predictions uncertain. While mathematical simulations offer valuable insights into the future movements of celestial bodies, they also underscore the limits of our ability to predict space events with complete accuracy. This brings us to an intriguing question. Why are prominent astrophysicists raising alarms about a potential crash between Pluto and Neptune now? Despite the various gravitational forces working to prevent such an event, experts like Neil deGrasse Tyson and Michio Kaku have expressed growing concern about a possible collision between these two planets. If Pluto and Neptune were to collide, it would be a significant and catastrophic event within our solar system. The crash would release an enormous amount of energy, likely leading to Pluto's destruction. Due to its smaller size and frigid composition, the debris scattered from the crash could create hazards throughout the solar system, potentially threatening the planets and their moons. For Neptune, the impacts could be significant as well, possibly altering its atmosphere and orbit depending on the nature of the collision. Michio Kaku, a a renowned theoretical physicist known for his work in string theory, offers an intriguing perspective on the situation. His research into the future of space exploration and the connection between celestial mechanics and theoretical physics provides valuable insights into the mysteries of phenomena like Pluto's orbit. Understanding the complex gravitational interactions that shape Pluto's movements can offer important lessons for future space missions. This knowledge will be crucial for better exploring our solar system, preparing for potential threats, and even planning missions to the farthest reaches of our solar system and beyond. The lessons we learn from studying Pluto's orbit can extend to our exploration of other distant worlds. By understanding how planets interact in space, we gain critical insights into celestial mechanics and the evolution of other planetary bodies. These discoveries can also support future space missions as we aim to explore other dwarf planets and trans-Neptunian objects. Pluto's unusual, erratic orbit challenges our understanding of planetary motion. It serves as a reminder that space is far more powerful and mysterious than we might have assumed. Celestial mechanics and string theory are intricately connected. The gravitational interactions and orbital movements of planets like Pluto and Neptune relate to the fundamental principles of physics. If Pluto and Neptune were to collide, it would be a groundbreaking event in the field of cosmology, offering an exciting opportunity for research that could even tie into string theory. String theory, which suggests that point-like particles in physics could actually be replaced by one-dimensional strings, aims to explain the fundamental forces and matter of the universe. A collision between Pluto and Neptune could generate extreme energy and gravity, potentially creating conditions where string theory's predictions may be observable. For example, such a high-energy event could offer a glimpse into the behavior of elementary particles and forces under extreme conditions, which is one of the key areas of study in string theory. However, the direct impact of a Pluto-Neptune collision on Earth would be negligible due to our distance from the outer solar system. The scientific implications could be extensive, though. It could significantly contribute to our understanding of the universe's fundamental nature, particularly in areas govern the movement of celestial objects. Their warnings underscore the importance of understanding gravitational interactions and orbital mechanics, which are critical to understanding our solar system. Pluto's orbit, characterized by its erratic shape and steep tilt, challenges conventional ideas about planetary movement. Unlike the nearly circular orbits of its neighbors, Pluto's path crosses Neptune's orbit at various points in its long journey around the Sun. The gravitational influence of Neptune and other planets is crucial in stabilizing Pluto's orbit, keeping it in a relatively stable position over centuries. However, predicting the future behavior of celestial bodies remains a complex and uncertain task. The possibility of a Pluto-Neptune collision, as suggested by experts, highlights the unpredictability and uncertainty inherent in planetary dynamics. While such an event seems highly unlikely in the near term, the gravitational interaction between Pluto and Neptune serves as a reminder of the delicate balance of forces in our solar system. The study of Pluto offers valuable lessons for future space missions, helping us explore other distant bodies and enhance our understanding of planetary evolution. NASA's New Horizons mission, launched in 2006, provided stunning images and data of Pluto and its moons during its historic flyby in 2015. The mission revealed striking details about Pluto's surface, including vast stretches of water ice and enormous fields of frozen nitrogen. These discoveries deepened our understanding of the geological processes shaping this distant dwarf planet. The success of the New Horizons mission exemplified the technological advancements and collaborative efforts necessary for deep space exploration. By studying Pluto and its moons, scientists gained valuable insights into the diversity of celestial bodies and the conditions at the outer reaches of the solar system. The outcome of the New Horizons mission embodied the innovative progress and cooperative endeavors necessary for profound space exploration. By focusing on Pluto and its moons, researchers gathered important knowledge about the variety of celestial bodies and the conditions at the farthest edges of the solar system. These discoveries have significant implications for future missions to explore other distant dwarf planets and trans-Neptunian objects, helping scientists learn about planetary formation and evolution. Pluto's classification as a dwarf planet has also sparked discussions about the criteria used to define celestial bodies within our solar system, reflecting broader questions about scientific classification and the evolving nature of astronomical knowledge. Understanding Pluto's orbit expands our knowledge of celestial mechanics and planetary dynamics, especially as we venture further into the outer reaches of the solar system. By studying Pluto's interactions with Neptune and other celestial bodies, we gain further insights into the formation and evolution of planetary systems. These insights are essential for developing theories about the origins of our solar system and understanding how planets and other bodies evolve over billions of years. Pluto's discovery and ongoing study have also contributed to our understanding of planetary motion and the development of the Kuiper Belt, a region beyond Neptune filled with small icy bodies. Studying Pluto's orbit gives us clues about the gravitational connections that may have shaped the formation of planets in the early solar system. This knowledge is invaluable for informing future space missions, including the search for potentially habitable worlds beyond our solar system. By studying the movements of distant celestial bodies, scientists can identify new targets for exploration and assess the feasibility of traveling to other star systems. Although the likelihood of a Pluto-Neptune collision is incredibly low, it serves as a reminder of the ever-changing nature of the universe and the consistency of large-scale cosmic events. As we continue to explore the far reaches of our solar system and beyond, the study of planetary orbits and celestial mechanics will remain a central focus for astronomers and space agencies. Pluto's orbit, which deviates significantly from those of other planets, offers important lessons about the complexities of planetary motion and the stability it maintains over long periods. Despite its whimsy, Pluto's orbit provides insights into the balance of forces shaping celestial movements in a broader sense. The continued study of Pluto's orbit and its potential interactions with Neptune reminds us of the challenges involved in understanding the universe. With each new discovery and each theoretical model, we refine our knowledge of the universe, uncovering the mysteries of distant worlds. The study of Pluto's orbit reveals even more significant lessons about the complex forces that govern our solar system. By examining how Pluto's path behaves in relation to other planets, especially Neptune, we gain crucial insights into the mechanics of space. These discoveries not only shed light on Pluto's past, but also help us predict future patterns in celestial behavior. Moreover, these studies have broader implications for understanding the evolution of planetary systems and the dynamic forces shaping their orbits over time. As the outermost planet in our solar system, Pluto's unusual characteristics and orbital behavior challenge conventional models of planetary motion. Although its renaming as a dwarf planet prompted a reassessment of what constitutes a planet, its unique orbital path has only expanded scientific interest. The study of Pluto serves as a powerful reminder of how much remains to be discovered in the farthest reaches of space. Through careful observation and advanced modeling, we continue to refine our understanding of how planetary bodies interact and influence one another, helping us appreciate the remarkable complexity of our vast universe. Pluto's relationship with Neptune, especially the intersection of their orbits, remains one of the most captivating mysteries in modern astronomy. Despite their orbits crossing at points, the two planets do not collide thanks to a delicate balance of gravitational forces. This stable interaction offers a glimpse into the sophisticated nature of orbital mechanics. Understanding how Pluto's orbit maintains its stability despite its turbulent inclinations provides valuable insights into the forces at play in our solar system and beyond. When researchers consider the possibility of a future collision between Pluto and Neptune, they highlight the enormous challenges of predicting the behavior of objects in such remote parts of the solar system. Even the most advanced simulations struggle to account for every variable, which speaks to the inherent unpredictability of celestial mechanics. Nevertheless, the very fact that Pluto's orbit remains stable despite its erratic nature suggests a level of cosmic order that is not immediately apparent. While long-term predictions about planetary interactions remain speculative, the current state of our knowledge allows for cautious optimism that Pluto and Neptune will continue to orbit safely for many years to come. The potential for a collision between these distant planets has captured the imagination of scientists and the public alike.